So Professor David Wallace holds the Mellon Chair in Philosophy of Science at the University of Pittsburgh, with joint appointments in the Department of Philosophy and the Department of History and Philosophy of Science. He earned his PhD in theoretical physics from the University of Oxford, where he also began his engagement with foundational and philosophical questions in physics. Before joining the Pittsburgh, he held academic positions at Oxford and the University of Southern California, spanning both physics and philosophy departments. Professor Wallace research focuses on the philosophy of physics with contributions to a wide range of topics, including quantum mechanics, quantum field theory, statistical mechanics, general relativity, symmetry and gauge theory, and quantum gravity. So he's especially noted for his work on the Everett many worlds interpretation of quantum mechanics, presented in his acclaimed book, The Emergent Multiverse, Quantum Theory According to the Everett interpretation, which is published in Oxford University Press in 2012. His broader philosophical interests include emergence and reductionism, structural realism, and decision theory, reflecting a comprehensive approach to the conceptual foundations of modern physics. Yeah.
Thank you very much for that very generous introduction, and it's a pleasure to be here this evening. Give me a moment while I share the slides for my talk. Okay, so there's a take on how to think about the interpretation of quantum mechanics, according to which, bluntly, it's a philosophical waste of time. And the starting point for that approach is some sort of idea that we all agree what quantum mechanics is. There are all these different interpretations of quantum mechanics. They're all a kind of verbal gloss on an agreed upon theory, and agreed upon formalism, and agreed upon way of doing physics, and that the right strategy is to shut up and calculate. What I want to do in this talk really is, partly to advocate ways of thinking about quantum mechanics that I think are helpful, but more than that, to try to say why, more generally, asking questions about the sort of foundations of quantum mechanics, how to understand quantum mechanics, is important, not simply from the sort of philosophical project to sort of understand and communicate the theory, although I think that's important, but also as something that feeds back into the practice of physics itself. Okay, so here's a starting point for this. Let's ask how we think about, or how we thought about theories of physics before the quantum revolution. So the way we thought about pre-quantum physics involves adopting something you might call the objective view of a physics theory. I think this is the view we had from Newton, from Galilei, that outside the quantum world is still how we think about physics theories. And the objective view says something like this. We have a system that we're studying. We represent that system mathematically. There is some state that system has, and the physical features of the system are represented by the state. So in classical mechanics, for instance, we have a phase space of possible states. A point in the phase space of the system represents where the particles of the system are and how fast they're moving, or what the density is of some fluid and what the pattern of velocities of that fluid is. And we have equations of motion. Mathematically, they tell us how the state changes over time, and because the state represents the physical features of the system, the equations of motion tell us how those physical features change over time. So the equations of motion determine trajectories in the space of states, and those trajectories represent physically possible histories of the system. Different states correspond to different ways the world could be, different histories correspond to different ways the world could unfold. There isn't a direct role for measurement in a theory of this kind. There are obviously important scientific questions about how we might measure or test any given scientific theory, but measurement is not built in to the very foundations of the theory. The theory isn't directly about what we can measure and observe, it's directly about what is going on. And when we study measurement as scientists, the goal of a measurement is to find out the objective pre-existing facts about the system state. So, the state represents the physical features of the system. Measurement tries to tell us what a subset of those features are. And in principle, nothing prevents arbitrarily accurate measurement. If we nudge the system unhelpfully, then sure, we'll disturb the system. For large systems, like if we want to measure where Mars is, we don't need to worry about that much. For small systems, like if we want to measure some strand of DNA, those things are delicate. We might well knock them if we're not careful. But there's no in principle barrier to simply passively learning the facts about the system arbitrarily accurately. And as I'm sure everyone listening knows, all of those features are hard at best to hold on to in quantum mechanics. But I think it's helpful to remind ourselves briefly why that is. So what happens to that objective view of a scientific theory when we start doing quantum theory? Well, notice formally it's got the right structure. I mean, quantum mechanics is still a theory of a state space, a space of Hilbert space V's or density operators, or however you want to think about it. It's got dynamics represented by the Schrödinger equation or by the path integral. Those dynamics do what we want dynamics to do. They give us equations of motion for how the state changes over time. At an abstractly formal level, this looks a lot like the objective view. But of course, as soon as we ask, how do we get content out of the theory, we go over to the Born rule, the probability rule, the mod squared amplitude rule. And that rule, as it's normally stated in our textbooks and our historical sources, explicitly introduces the notions of measurement and observation into the theory at the level of how the theory is written down and formulated. So it's no longer the case that measurement is something external to the system that just reports on the facts about the system. Measurement is formalized in the theory itself. So to look at the classic form of a measurement in quantum mechanics, if I've got some observer X, some observable X, that very word observable kind of gives the game away a little. If I have an observable X whose spectrum is some set of eigenstates Xi with eigenvalues Xi, and if I decompose the quantum state of the system as a superposition of those eigenstates, we can't understand measurement of X as just telling us passive facts about the system. The measurement's going to return some actual value of the possessed quantity. The quantum state doesn't seem to represent an actual value of possessed quantity. It seems to be a superposition of many values at once. So whatever measurement is, it's not simply telling us some objective property of the system as represented by the state. So what do you do about that? How do we understand quantum mechanics, given that this kind of straightforward, naive, objective view of the theory isn't available? Well, a lot of philosophers and not a few physicists over the century we've had quantum theory attempted to say, well, look, if the theory doesn't do that, so much the worse for the theory. The theory is some kind of algorithm that gets the answer right, but it's not really a scientific theory in good standing. The idea here would be something like it's constitutive of a good scientific theory that we can take the objective view for it. If we can't take the objective view to this theory, we need to replace the theory with another theory to which you can take the objective view. So conceptually, philosophically, that position is impeccable. The only little problem with it, of course, is that quantum mechanics is kind of successful. The theory's done extremely well for 100 years. Attempts to modify the theory, to change its equations, to supplement it with more equations, those have not been conspicuously successful. We have toy theories that try to modify quantum mechanics to let you take the objective view in it. They work okay, arguably, in the non-relativistic regime. Extending them to the full panoply of quantum field theory, that's the language of our best contemporary physics, has proved difficult at best and hopeless at worst. There are still principled projects trying to pursue this, but in accordance with the mainstream view in physics, I'm going to set those projects aside and say, we can't change the quantum formalism, we have to make sense of it. If the objective view is not a way of making sense of it, what's the alternative? So there's an alternative that's been in the literature since the inception of the subject, and which still turns up a lot in undergraduate level textbooks on quantum mechanics. And you might call this view the lab view, laboratory view. And according to the lab view, but again, I want to clarify what I'm saying here is, given the formalism of quantum mechanics, if we can't understand it as just objectively describing the evolution of the properties of a system separate from us as observers, how can we understand it? So the lab view is one rival alternative we might try to use to make sense of quantum mechanics, and indeed which physicists have used to try to make sense of quantum mechanics. And the lab view basically goes something like this. We say any application of a physical theory is relative to a fixed experimental setup. In other words, from the lab view's starting point, and you can see these ideas in Bohr's work, from the lab view's starting point, we can't simply describe the world as is. We have to describe the world, or a part of the world, relative to the experimental setup by which we wish to interrogate the world. And when we talk about an application of a physical theory, we mean by that something quite stylized. We mean something with three steps. We mean, firstly, the system is prepared in some state. And that on the lab view is taken as primitive. The lab view doesn't ask, how did the system come to be in a certain state? It just posits that it is. Then there's dynamics. We evolve the state forward under the Schrödinger equation, or whatever approximation to the Schrödinger equation we use. That's not primitive. That's the core of the theory. Then we measure. That too is primitive. Here we simply apply the Born rule. The measurement process is not treated as just more physics. It's treated as external to the quantum framework. And that kind of basic paradigm is there in a lot of the ways people think about quantum theory. So, for instance, the kind of operationalism that Werner Heisenberg used to make sense of quantum mechanics at the dawn of the subject, and that physicists like Asher Perez have carried forward to more modern work, says that's it. There's no further interpretation to do. Quantum mechanics is an operational calculus. It's a gadget to predict what experiments do, nothing less, nothing more. Most people, physicists and others, haven't been happy with that. Niels Bohr was not happy with that. Bohr had something subtler in mind. Bohr thought we can make sense of quantum mechanics on the lab view as describing features of a system, but those features only possessed relative to an experimental setup. So we can talk about particles and their positions, but only if our experimental setup is trying to measure where particles are. We can talk about waves and interference, but only if our experimental setup is trying to measure those interference effects. And so the possession of properties by a system is not absolute and independent of measurement. It's relative to those measurement contexts. And there is a complementarity between different descriptions. They're incompatible, but that doesn't leave a contradiction because we can only use those descriptions relative to a certain experimental setup. In more recent foundations of physics, I think you've had a talk by my friend and colleague Chris Fuchs. The cubists take ideas of operationalism and complementarity and sort of modernize them and bring them into a quantum information context. I won't talk in detail about their approach, but the underlying idea is, again, that measurement is kind of external and basic, and the quantum theory is a theory of measurement and interaction with systems and not a feature of objective properties evolving. And of course, if you look back again to the inception of the subject, the ways of describing quantum mechanics due to Dirac and von Neumann, and we'll still find in the textbooks, suppose that the measurement context directly affects the dynamics of the theory, so that the Schrödinger equation is not, after all, the exceptionless description of a system's dynamics. It's interrupted by the process of measurement, and that process of measurement uncontrollably, randomly, stochastically kicks the system into one state or another. Now, in most of these examples, the last is perhaps an exception, the quantum state isn't being understood as describing objective facts, as in the objective view. It's not representing the physical features the system actually has. It's representing our partial knowledge of those features. When we say that the system is in a superposition of spin up and spin down, it's not that that is some property the system has. It's some indirect way of saying maybe it's in spin up, maybe it's in spin down. Or perhaps maybe our measurement device will say spin up, maybe it will say spin down. Now, philosophers and physicists have worried about the idea that somehow this lab view of quantum mechanics, this experiment first view of quantum mechanics, somehow isn't what we want of a scientific theory, that somehow it's part of the nature of what we want from science, that we should have something closer to the objective view, something less about how we intervene and interfere with a system, more something about what the system itself is doing, what the world is actually like. I'm sympathetic to those concerns, but really what I want to say in this lecture is never mind our philosophical concerns about the lab view. The lab view of quantum mechanics, while it's great for some context, for some problems, is not ultimately broad enough to make sense of the way we actually apply quantum mechanics in the practice of physics. I want to spell out a few ways that plays out. So firstly, let's talk about some limitations of the lab view when it comes to modeling real experiments we do in physics. And there's a common theme of the points I'm going to make here, which is there's something a bit paradoxical about the idea that measurements are external to the quantum formalism. Because after all, if you go to your experimentalist colleague down the hall and ask them to build a device that measures some property of quantum mechanics, they don't just go to the shelf and pull off a black box that has been stamped, I measure this self-adjoint operator. They build a gadget using detailed principles of physics. And increasingly, those principles of physics are principles of quantum physics. That is, the state of the art in measuring quantum systems these days has far transcended big, bulky things themselves built classically. Modern measurement devices use quantum mechanical ideas themselves. That is, the actual practice of physics doesn't seem to be a practice where measurement is external to quantum physics. It seems to be a practice where we need quantum physics to analyze measurement itself. But let me show a few sharp places where that plays out. So here's one of them. In the lab view of quantum mechanics, the natural paradigm is we prepare the system, we evolve it forward, we measure it. But what about if we want to measure it more than once? What about if we want to measure what the particle's spin is and then 10 seconds later measure it again? Well, naively speaking, the lab paradigm doesn't say much about that at all. We could say that we could appeal to the notion of wave function collapse and say the way you measure multiple measurements is that the wave function collapses onto an eigenstate of the operator being measured. This is what we learn in quantum mechanics first classes. And then we could use that to try to understand repeated measurements. But it's been known for a long time that really repeated measurements generally disturb systems. So for instance, the typical measurement of a photon by a photoplate destroys that photon. You can't measure where the photon is again because it's gone. But why do we know it destroys the photon? Because the physics of measurement says so. So the reality of modeling repeated measurements is the details of the physics really matter and have to be included in the modeling process. Similarly, if you ask yourself, how about continuously observing systems? If you go back to Schrodinger's classic example of the cat, Schrodinger puts his poor feline in a box. The box has a Geiger counter in it. The Geiger counter is connected to a sample of a radioisotope. There's no sharp, discrete measurement where we kill the cat if we get spin up and we leave the cat alive when we get spin down. What really happens is it's a continuous process where the Geiger counter is continuously measuring the system being measured. And at the point at which it measures that there's been a decay, the poor cat gets killed. It's hard to see how one models that in this framework that simply treats measurement as external. In fact, if you try doing it naively, if, for instance, you appeal to the collapse of the wave function, you find your way to Zeno's paradox, the quantum Zeno paradox. You find that the very act of continuously observing a system, if you analyze it naively, without attention to the physics, freezes the system in place. So the lab view of measurement as external to the physics really struggles with these detailed features of physics. of the measurement context. Now, we could take from that somehow that says obviously there's something wrong with quantum mechanics. But the reality is we do quantum mechanics perfectly well to handle these problems. And in fact, here is how we use quantum mechanics to analyze measurement. We expand the quantum description to include the measurement device. This often gets called the church of the larger Hilbert space. So now we don't just have the quantum theory of a spin, for instance, evolving by itself. We have the quantum theory of a spin dynamically coupled to a larger measurement device with macroscopically many degrees of freedom. We evolve all of that by the Schrödinger equation. Then we apply the Born rule to the macroscopic degrees of freedom of the device, which we treat now not as being properties that are inextricably associated with measurement and observation, but probabilities that are objectively possessed by the system. And if we do that, if we analyze quantum mechanics this way, we find that we can understand the building of measurement devices perfectly well. We can understand how measurement devices that are not built by classical principles, but are built by quantum principles themselves, how they work perfectly well. We can analyze repeated and continuous measurements perfectly well. We can find, for instance, that what really matters in continuous observation, if we worry about the quantum Zener effect stopping things evolving at all, is not are we measuring continuously, but what is the response time of our measurement device relative to the evolution time of the system being measured. We find that in the limit, where the measurement device responds very slowly compared to the physics of the system being measured, that essentially the system being measured will just do its own thing and the measurement device will not matter. And Geiger counters react very slowly to radioisotopes relative to the timescales of radioactive decay. We find at the other extreme that if a measurement device has a response time that is fast compared to the evolution time of the system, then it's genuinely true that the dynamical coupling to the measurement device suffices to slow or even stop the evolution of the system. We can predict that quantitatively. We can test it in the lab. We could do some beautiful physics. But again, we're doing physics here that transcends that lab view of physics. So what that tells us is that to understand and do physics, to make sense of our experimental state of the art, we need to step beyond the lab view and have a better way of thinking about quantum mechanics. The lab view's been great for some stylized problems. It's wonderful in quantum information, for instance. But to make sense of quantum mechanics writ large, we need something broader, something that will have the lab view as some special case at best. There's another set of reasons for that, which give us more of a hint as to where we might go further. So far, I've been talking about the kind of context of the experimental physicist, doing a stylized experiment in the lab. But many areas of physics are cases where we're not doing a discrete experiment where we prepare the system, do some stuff to it, and then go home. We're studying some ongoing, objectively treated historical process. So, for instance, if we're interested in the luminosity of the sun, that's a quantum problem. The luminosity of the sun depends on the quantum tunneling processes that govern the speed of fusion reactions in the core of the sun. We have to do quantum physics to study the sun. But we're not studying the sun in the lab. The sun is an ongoing, evolving system. We understand its luminosity over the billions of years it's existed through a sort of inverse problem solution where we map our best theories of the stellar interior and the stellar envelope to what we learn from geological, paleontological data about how luminosity has changed over time. Only in the most Procrustean sense can we really say that a best fit to paleoclimate data counts as a quantum measurement of the core of the sun. Similarly, if we look at the nuclear weapons tests in the atmosphere in the mid-20th century and the radioactive fallout those experiments led to, and their effects on cancer rates and other health issues, and the degree to which they still show up now in the biosphere, that's an ongoing process where quantum mechanics is playing an inextricable part, and yet it doesn't fit the standard paradigm of the application of quantum physics. And to give a more explicitly quantum mechanical example, if we look up into the night sky And we see the inhomogeneities and the anisotropies that we see in the cosmic microwave background radiation and later in the distribution of galaxies. Our best theories of where that structure comes from are quantum mechanical. We think that structure is a relic of the quantum fluctuations in the early universe. But again, we can't really say that our sophisticated, complicated, very computationally intensive models of structure formation should simply be interpreted as a quantum measurement of the inflaton field in the first moments of the universe. So this too points us to a way of thinking about quantum physics that somehow recovers more of the idea of quantum physics describing objective processes playing out, not or not only because that seems philosophically necessary, but because it seems scientifically necessary. So what might that look like? Well, the common theme is the one we already saw in understanding how we modeled physical quantum experiments, which is that in lots of contexts, we do seem to want to read the quantum state probabilistically as describing objective probabilities. What we normally seem to do in applications of quantum mechanics is say, look, the probability distribution given to us by the Born probability rule over macroscopic degrees of freedom, whatever that means, and we'll come back to it, that is objective. Or at any rate, it's as objective as the probability distributions we use in statistical mechanics. When we say that the probability distribution over states of, let's say, for instance, a pollen grain undergoing Brownian motion in equilibrium, when we say its probability distribution is given by the Maxwell-Boltzmann distribution, how objective that is a subtle and contentious matter. But at the very least, quantum probability distributions are treated as objective as that. They're the kind of things we can measure through frequency data. But of course, if we could do that consistently all the way down, we could treat quantum mechanics as a whole as just like statistical mechanics, just as telling us the probabilities that the underlying systems have certain positions of momentums. We know we can't do that. The core of quantum theory is interference. It's the fact that the particle going through two slits at once can't be treated as either going through one slit or the other. Because if we ask how likely it is to end up being measured in some location conditional on going through the first slit, and how likely it is to end up in some location conditional on going through the second slit, and we just sum those in accordance with the ordinary rules of probability, we get the wrong answer. We have to interfere the two outcomes. And a wealth of work in the foundations of quantum mechanics in the centuries since it was created, the Kochen-Specker theorem, the Gleason's theorem, the PBR theorem, have shown us how simply reading quantum mechanics objectively as a probability theory is enormously difficult at best, probably impossible. I have colleagues who still fight to try to achieve it, but at the very least, there are profound headwinds in trying to do that. And the reason, of course, as any undergraduate knows, is that at a fundamental level, quantum mechanics is not a probability theory, it's an amplitude theory. And these amplitudes are a weird and strange and new thing that can't just be understood as probabilities, can't be understood in terms of partial knowledge or ignorance or relative frequencies or however you want to think about probability. But crucially, in most physical applications of quantum mechanics, we're not working at a fundamental level. We're not doing the full quantum mechanics of every last degree of freedom of the inflaton field or the center of the sun, or even the macroscopic device we're using to measure the spin of a particle. Mostly we're working at an emergent, much higher level. And that brings us to what you might call the decoherent view of quantum mechanics, which is that somehow at this higher emergent level, we recover things that can be understood as probabilities. Decoherent because at that higher level, we can see that the coherences, the quantum interferences that get in the way of any attempt to understand quantum theory as a probability theory go away. This decoherent view is an alternative to the lab view, an attempt to get closer to, if never quite reaching, the objective view of pre-quantum physics. And according to the decoherent view, the way we extract empirical content from our physical theories is something like this. We derive approximately autonomous equations for certain higher level degrees of freedom, macroscopic degrees of freedom, in regimes where those autonomous equations are deterministic or at any rate stochastic. Decoherent regimes where the interference that spoils any attempt to understand quantum mechanics is suppressed. And then when we're in those regimes, when we have those high-level dynamics, we interpret those via the objective view as giving the probabilistically objective information about what the state of the system really is. So for instance, when we're studying measurement processes, we're interested in the macroscopic degrees of freedom of the measurement devices. Where is the pointer pointing? What does the digital readout actually say? Where has the center of mass of the device moved to? We abstract over, we trace over, in technical terms, the microscopic degrees of freedom of the devices. When we're studying the core of the sun, we're really interested in its bulk thermal properties, abstracting over the vast number of compatible microstates. Those decohere. When we're studying cosmology, we're not interested in every last degree of freedom of the inflation field. We're interested in the low wavelength modes that give rise to the primordial inhomogeneities that seed the galaxies, abstracting over the high wavelength degrees of freedom in the other fields present. And where do we get this higher level autonomy from? Where do we get the fact that even while quantum mechanics as a whole is a theory of amplitudes and not probabilities, a theory that cannot be understood probabilistically, nonetheless its higher level degrees of freedom can be understood probabilistically? Well, sometimes we get that because the higher level degrees of freedom decouple entirely. If I just have the center of mass of some object moving freely, then as any undergraduate knows, I can decompose the degrees of freedom into a center of mass degree of freedom, obeying a free Hamiltonian, and all the residual degrees of freedom. But that's not a stable source of autonomy. It's not stable under interaction with other systems. Much more commonly, we have what you might call statistical autonomy. We can average over the residual degrees of freedom. When we do that average, we get autonomous degrees of freedom, but we get degrees of freedom whose dynamics are decoherent, no quantum interference, and time irreversible. And it's in that statistical autonomy regime that we recover the probability reading of quantum mechanics. And in doing that, we need to distinguish between two sources of autonomy, of statistical autonomy. Sometimes it comes from what physicists like Wojciech Jurek have called environment-induced decoherence, where, for instance, a dust grain might be decohered, might lose its quantum aspects through interacting with the air around it, or the sun's radiation, or even the microwave background radiation. That's one source of statistical autonomy, of decoherence. The other source is when a system's own small-scale degrees of freedom suppress interference. You can't do interference experiments between a live cat and a dead cat. You can't somehow send the live cat through one slit and the dead cat through another slit and somehow cancel out the dead possibility and reinforce the live possibility. Why not? Because all the other degrees of freedom of the cat are repeatedly, redundantly recording whether the cat is alive or dead. So that trying to re-interfere the live cat and the dead cat would be as impossible as trying to time reverse the equations of a macroscopic statistical mechanical system. All right, where does that leave us? I've argued that to do physics in the modern regime, to handle a situation where quantum theory is all over our physics and not just confined to certain areas which we can measure classically and treat measurement as external to it, we need this decoherent view of quantum mechanics. We need to treat quantum mechanics as a self-contained theory from which we extract higher level autonomous dynamics that we can treat probabilistically. All of that is physics in the sense that all of that is a practical structure for how we can do physics. And now we can ask ourselves, how do we make sense of that structure? It was easy enough to make sense of the objective view. The objective view said physics is about what the system's actually doing. It was easy enough to make sense of the lab view, although there were many rival ways of doing it. At some level, physics is a calculus of experiment and observation. How do we make sense of this decoherent view? Well, this brings us to the Everett interpretation, and to Hugh Everett's work in the 50s, but transformed by the development of the theory of decoherence in the 70s and 80s. Here's how it goes, if we want to make sense of the theory. Ultimately, fundamentally, this is a theory of amplitudes and interference. And because of that, we can't treat it as a fundamentally probabilistic theory. But we can get content out of the theory. We can consistently apply the Born probability rule via the regimes in which we can emergently interpret the theory as a probabilistic theory. We learn about those regimes by studying the dynamics of the full theory then. We can't get out those emergent dynamics unless we study the full theory and work out in some detail just when the microscopic features can be averaged over successfully. And we do all that without any measurement context in play. We're just studying the unitary evolution of the system. And since we need the full theory to make sense of quantum mechanics, we need to take that full theory's dynamics seriously. And of course, those full theory's dynamics are not probabilistic. They involve interference and amplitudes. And from all this point of view, then measurement has gone back to something much closer to what it was in the objective view. It's a special case of high-level dynamics. A measurement process starts by initially magnifying up a low-level superposition to a high-level superposition, and then finds that the interference that might occur at that high level is suppressed, and that we have an autonomous dynamics for the macroscopic degrees of freedom that record the initial magnified microscopic degrees of freedom. And at the physics level, that's the core of the Everett interpretation. But of course, the Everett interpretation famously, and as the original title for this talk shows, is often called the many worlds theory. And the rationale for that is that if we take quantum mechanics literally in this way, and if we treat the quantum state as fundamentally objective, not fundamentally something that can be read probabilistically, only emergently something that can be read probabilistically, well, it follows then that systems can really be in macroscopic superpositions. Nothing fundamentally distinguishes 1 over root 2 spin up plus spin down from 1 over root 2 cat is alive plus cat is dead. Probability is only emergent, hence the title of my book that you were kind enough to mention in the introduction, The Emergent Multiverse. Parallel worlds are not fundamental in Everett's interpretation. There's something that turns up emergently, approximately, at a high level. Fundamentally, you have interference and amplitudes, and yet fundamentally that means we still have macroscopic superpositions. And look, at some level, it's worth saying that, and this goes back to my points at the beginning, it doesn't really matter for most scientific purposes whether you take literally seriously the fact that macroscopic superpositions are physical, or whether you simply think of them probabilistically once they get to the macroscopic level. The slogan, of course, is shut up and calculate. But I think it's worth seeing that when we say shut up and calculate, we're shutting up and calculating inside this decoherence-based Everettian way of doing quantum mechanics. We're still using the Everett interpretation. We're just choosing not to believe all of it. And that might be fine. That might be even scientifically legitimate. It might even be sensible. But nonetheless, we're working in a way of thinking about quantum mechanics that's very different from the way that we might have got from Bohr or Heisenberg. From a scientific point of view, the key principles of the Everett interpretation are dynamics is always unitary. When dynamics appears non-unitary, it's just because we're confining our attention to some subset of the degrees of freedom. Measurement is just another physical process. The observer plays no special role. That idea inherited from the objective pre-quantum view of physics. And the transition from the quantum to the classical world is not something to understand in conceptual or metaphysical terms. It's the dynamical suppression of interference. Okay, so I'm mostly done now. Let me wrap up. I said at the beginning I wanted to say how interpretation matters, how it's not simply a verbal gloss on an agreed upon framework. And part of what I've tried to show here is the very way we formalize and use quantum mechanics turns on some of these questions about how we make sense of it. Can't be separated from these questions as to how to make sense of it. We've seen three things we might do to make sense of quantum mechanics, to take the sort of initial practice that was coalescing in the 1920s and make it into a theory we can understand, we can use, we can teach. The first possibility is we could say the theory is deficient. We can modify the theory. I've said that ultimately I don't think that's viable, but I think it's very important to know that the project of trying to modify quantum theory has led to a great deal of knowledge about the theory. It's led to a plethora of no-go theorems. Most famously, it's led to Bell's inequalities and the ability to relatively directly test the non-locality of a theory. It's given us a way to parameterize how we might test quantum mechanics, how we might put empirical constraints on the universality of the superposition principle and the Schrodinger equation. A lot of good testable physics has come out of the idea that we might modify the theory. We looked at the lab view, and I argued again that I thought the lab view ultimately wasn't viable as a way of thinking about quantum theory, but it's still been profoundly helpful and useful. Large amounts of quantum information, arguably the success story of quantum theory of the last 30 or 40 years, has used implicitly or explicitly something like the lab view. And it's given us an enormous amount of insight about the subtle and different ways in which quantum mechanics is kind of like and yet kind of not like a theory of probability and information. And the decoherent view, even internal to quantum mechanics, has led us to a deeper understanding of the quantum Zeno effect, has led us to decoherence theory. Through David Deutsch's exploration of parallelism, it led us to the foundations of quantum computation itself, as well as it being a sort of foundation for the general way in which we apply quantum mechanics in regimes ranging from solid state to cosmology. These are fundamentally different ways to do quantum mechanics. They're not just verbally different. They've all led to scientific progress. That said, it's the decoherent view, and hence the Everett interpretation of quantum mechanics, the view that we treat quantum mechanics as unitary, that we treat macroscopic superpositions as not different in kind from microscopic superpositions, that we treat the theory as not fundamentally a probabilistic theory, but emergently a probabilistic theory, that we treat measurement as just one more piece of dynamics, that we treat the quantum classical transition as one more piece of statistical physics. It's all of that that underpins the great bulk of the contemporary applications of quantum theory. And I'll stop there. Thank you very much. There are a few references here for people who want to follow some of these ideas further. Thank you.
Thank you very much, Professor David, for that insightful lecture. Without any delays, we will take up a few questions. Questions asked by Dr.
Good.
Bharat Government PG College, Raniket, Uttarakhand, India. So the question is, sir, with the emerging quantum technologies shaping the future from quantum AI to quantum sensing, do you think adopting the many worlds interpretation can lead to the new ways of engineering devices that actually exploit parallel branches, not just probabilities? Could this shift how we design future quantum systems?
Yeah, that's an excellent question. So historically, it's definitely true that thinking in terms of the many worlds theory was valuable in developing these quantum ideas. I mean, the idea that somehow quantum parallelism was going to be exploited was at the core of Deutsch's original conception of quantum computation. And arguably, the Shor algorithm, one of the most striking applications of quantum information, likewise turns on parallelism. It relies on the idea, effectively, you create a superposition of different possible computational inputs. You do a classical computation in parallel, and then you do a clever interference experiment to extract some collective property of that. And when I was a PhD in physics, I was initially working in quantum computation not long after these ideas had come out, and the widespread view there was very much that quantum parallelism was going to be this route to understand how to get power out of quantum computers, and that Shor's algorithm was just going to be the beginning of a vast family of algorithms of this kind. Now, it's fair to say that idea hasn't really panned out. It hasn't been that straightforward to extract algorithms in quantum theory from the parallelism idea. And in fact, most of how we would think about applying quantum computers now, if we had a quantum computer tomorrow, what would we do with it other than factorize large numbers? The answer is mostly that we'd simulate other quantum systems. And I think one way to think about that is that the regime in which parallelism is a helpful way of thinking is this kind of emergent classical regime. We get parallelism in a situation where the deeply quantum aspects of quantum theory are suppressed by decoherence. And what we mostly would be able to get from a quantum computer is a device where we could control it in the way we control computers in a regime that is not decoherent. And so we would be using that to explore features of quantum theory which just don't fit that emergent multiverse, emergent multiplicity framework. So in some ways, I think the power of quantum computers reflects the idea that the world is not fundamentally a many worlds theory, but only emergently a many worlds theory. So while it would be great as a piece of propaganda for the position I've defended to say, yes, absolutely, parallel universes are the way to think about quantum information, in many ways, I think it's more or less been the opposite. Quantum information has shown us the degree to which the parallel universe way of thinking of quantum mechanics is applicable only in this kind of macroscopic emergent regime with rare exceptions.
The second question is being asked by Shravan Kumar V, Bhaktivedanta Institute, Calcutta. In a universe where every possible decision plays out in some branch, does it still make sense to say we choose freely?
Okay, so I want to worry a little bit about the idea that indeed every possible decision plays out in some branch. So if there's some choice I make that I make quantum mechanically randomly, let's suppose I decide to have, shall I have cereal or toast for my breakfast this morning? Sorry, in the US it's still morning. Then it's certainly true that there'll be a branch in which I had cereal and a branch in which I had toast, but that arguably just shows that choices I make randomly, whimsically, are not really the paradigm example of my freedom to act. When I walked into the office to give my talk, I didn't decide to strangle any passers-by. That's not, I hope, because I decided through some quantum random whim not to strangle somebody, and in another branch I just chose to strangle them. I'm pretty confident that insofar as you can treat me as a physical system at all, then I deterministically decided not to strangle the person. Now, sure, there's probably some branch in which some weird brain aneurysm caused my muscles to move in some sporadic way that strangled the person, but that isn't the playing out of my action. That's just some freak piece of bad luck. So I don't really think genuine free choice is undermined by the Everett interpretation. I think perhaps a useful thing to say here is that I think there are deep puzzles about the compatibility of free will with mechanistic physical theories that say objectively how things evolve over time. And that's led to a lot of philosophical discussion, a lot of debates about compatibilism versus hard determinism versus libertarianism, blah, blah, blah. I think that's a deep and interesting area of philosophy. I have opinions in it. They're not terribly original. I don't think the many worlds theory changes that very much. I think ultimately, and this is actually something that happens a lot, it's not just true for free will. Ultimately, the many worlds theory reminds us of some deep philosophical problems that were already problems by throwing it into this new and alien context. It's not generating new problems there.
So the third question is by Jawahi, IIT Jammu, India. What is the spin at last? No classical analog. How is that consistent with it?
So yeah, because the spin is, of course, so to speak, a classic example of a property that just doesn't have a classical analog. Spin, I suppose that it has a kind of analog. Spin is kind of like angular momentum, but it's not angular momentum. It's fundamentally quantum. And it's not the only property that's fundamentally quantum. In quark color is fundamentally quantum. A whole bunch of weirdnesses in solid state physics and high energy particle physics are fundamentally quantum. We can mathematically model these things, but we can't describe them in classical language. I think that just tells us that quantum theory is a genuinely new theory. It's not just a descriptive calculus for things that can be understood classically. There is genuine conceptual novelty in quantum mechanics. New ideas turn up in quantum mechanics. How do we come to understand those ideas? How can I tell you what spin is? Well, I think this is a special case in general of how I can explain a conceptually novel idea in a scientific theory to someone. You can partially try to rephrase them in classical ideas. Again, the first time you learn about spin, you learn it's kind of like angular momentum, even if it's got some features that's different. You get a partial intuition of what it is through that way. Eventually, you understand the theory well enough that you kind of know what it is in its own terms. You could say the same about classical contexts, like what's space-time, what do we mean by the curvature of space-time, what's gravity. These are notions that we kind of initially learn through kind of analogs of our experience, and then eventually we get familiar enough with them that we know and understand how to use them. And at some level, arguably, there's no more to understanding, this is a general philosophy point, no more to understanding what a word means than fully knowing how to use it in the right contexts. I mean, if I asked you to define any word in a natural language like English, the definition never gets at exactly what the word means. You only ever really understand exactly what the word means when you know how to use it fully in context. I think one lesson of philosophy has been there isn't some permanently understood, permanent core of ideas such that we will always and forever be able to explain new ideas in terms of those new ideas. We have to gradually learn new ideas through understanding how to use them. And I think fundamentally spin is no different from that.
Number 4 is being asked by Professor A. Aliwal, SBS Government PG College, Rudrapur, India. So in today's quantum technologies, controlling decoherence is crucial, yet the decoherent view explains how classicality itself emerges. How can insights from decoherence theory actively guide the next generation of quantum computing and quantum error correction research?
Yeah, I mean, I wish I had something more sophisticated to say here. At some point, this is the problem with being a philosopher of physics, rather than somebody working closer to the cutting edge of the applications of these particular ideas. As you say, from the point of view of building a quantum computer, decoherence isn't an interesting thing that happens. It's an active threat. It's a problem that occurs that we have to kind of control and manage away as much as possible. If I had specific suggestions as to how that could be done, I would probably be in a slightly different line of work. What I think understanding these things can contribute is it can just mean that the people who are trying to do the more detailed understanding and modeling can get a cleaner idea about what's going on in the decoherence process and what are the ways in which you can identify degrees of freedom that are in various ways resilient to decoherence. So one example of how I think that kind of thing helps, at admittedly a quite high level of abstraction, is, and I touched on this briefly in my slides, one way you often think about decoherence is something like you have a fixed split between system and environment. Often it's delivered spatially. Often you've got some physical system sitting here, and then in a different region of space, there's an environment. And then decoherence is somehow explaining why this quantum system in its entirety is evolving non-unitarily, is having its interference suppressed by this system in its entirety. And that's sometimes an important aspect of decoherence. But equally often, I think probably more often, what's really going on is the decoherence. You want to understand the decoherence internal to this spatial system. What's going on is I've got some subset of degrees of freedom of the system, sort of collective degrees of freedom, like low wavelength modes. And those degrees of freedom are being decohered by all the high wavelength modes. So if you're doing sort of quantum solid state terms, you can think that I could treat the low wavelength modes as something like classical degrees of freedom interacting with a gas of short wavelength phonons. And when you realize that, you start saying, well, what makes a given decomposition the right decomposition? It's precisely the fact that there's no that the decoherence gives you autonomous dynamics for these degrees of freedom. So a lot of that, I think, shades into pedagogy. I hope that understanding these ideas makes it easier for the sort of new generation of PhDs and postdocs who are going to have the brilliant ideas that actually help us build these amazing pieces of technology to have a clearer starting point that makes it easier for them to progress those sets of ideas. But I wouldn't want to pretend that the kind of philosophy of physics I do is contributing other than at one remove to those larger projects, or those more specific projects, I should say.
So question number 5 is being asked by Vasudev Rao, Bhaktivedanta Institute, India. So what kind of advances in quantum mechanics would enable all of us agree on the quantum reality? Do you see such a day will come?
Good. Yeah. So this sort of links to the distinction I was making between ways of doing quantum mechanics and then the interpretation of quantum mechanics. I think, and I'm optimistic that we are converging on, we will converge on a consensus that we teach in textbooks that the way we should think about quantum mechanics is according to what I was calling the decoherent view. And the kind of advances that drive that, I think, are scientific. They're the degree to which the lab view of quantum mechanics is insufficient to really think about quantum mechanics. And so as long as we teach quantum mechanics in terms of external, outside observer, collapse of the wave function, and we don't sort of embed these ideas about decoherence and quasi-classicality and dynamical transitions into physics pedagogy, then there's going to be an increasing mismatch between what we learn and teach our students and the way they apply the theories as it comes out in realistic applications. And so I think we can expect a convergence. Well, I think we are having, and we'll expect a convergence on that way of doing quantum mechanics. Now, are we then going to converge on an agreement as to whether this is really a many worlds theory or a theory that's just usefully described in language of sort of branching? That I'm less positive about. I think, in a way, that almost becomes more like the question of, do we think our theories are true, or do we just think they're sort of useful pretenses? I mean, philosophers discuss that question, but it's arguably not that directly salient to physics practice. But I think that would still be a lot less confusion and a lot more clarity than we have had through the second half of the 20th century.